Howdy guys. So I'm back with another little video here, and I'm going back to some thermodynamics in juxtaposition to my other uploads that I've made recently in terms of physics. Predominantly, I'm going to be looking at, or really continuing, what we were covering in Rife, and I've decided to kind of change pace a little bit, look at a little bit of a different textbook here. Namely, we're looking at Fitzpatrick today instead of Rife, because Fitzpatrick had a very nice, concise explanation of all these. Just kind of lined up like ducks in a row. Now, this particular portion of StatMech, personally, for me in undergrad, kind of got me tripped up because I wasn't really too certain what these were used for or why they were helpful. They were just kind of tossed at me a little bit, and I just didn't really understand it, but I've come away with a little bit of a better understanding of how this works, because now I also have a better understanding of how calculus works as well. But besides the point, we're going to be basically just deriving our four Maxwell relations, which are very handy for relating the state functions of enthalpy, Helmholtz free energy, Gibbs free energy, internal energy, to their parameters like temperature, pressure, entropy. And then when we do these derivations, what we're going to see is that we can actually relate a measurable quantity to a theoretical property, which is really good. So if we need to know what some change is with the system for some theoretical property, we know that it's equal to some other actual tangible property, which allows us to make really unique and good measurements in the lab if we're doing some sort of research, right? And if I'm not careful here, I might have a visitor jump up on top while I'm trying to give an explanation. Besides the point, for the first function that we're going to look at, we're going to look at internal energy. And internal energy, if we remember from the first law of thermodynamics, can be re-expressed in terms of entropy and volume, right? Because this would be our dq, and this is just our dw, if you remember that, right? So with that in mind, bumping a ruler over here, we can also mathematically express this small change of energy in terms of partial derivatives of the parameters of the function itself. This ds and dv tell us that energy is a function of entropy and of volume. So we say that it's equal to the partial derivative of this volume with respect to that variable, with the other one held constant, times some infinitesimal change in that parameter, plus the other one, so on and so forth. This would repeat ad infinitum, I believe, for functions of 3 variables, 4 variables, 5. Double check me on that. If I'm wrong, shred me like cheese in the comments, please. But besides the point, what we can notice from this when we do direct juxtaposition of the mathematical and the thermodynamic equations, we notice that our temperature is equal to the partial derivative of E with respect to the entropy, and our negative pressure term is equal to our energy partial derivative with respect to the volume. Now, with a handy little thing with Fubini's theorem, which just basically states that for some functions, and I don't remember what the exact qualification for these particular functions are, but it's a handy relation that can help us link the relationship between the two parameters. And I'll remind myself to put a little comment about what Fubini's theorem actually is. I just remember the name, but basically by Fubini's theorem we can say that the, I think it's for inexact and exact differentials. But we know that this has to be some sort of exact differential equation, because the partial derivatives of E in either order with respect to volume and then entropy, or with entropy and then volume, those are equal to one another. So if we had some expression for energy with parameters S and V somewhere along the lines, and we did those partial derivatives in that order, we're going to get the exact same expression. So we can basically break off the partial derivatives, segment them out to really isolate our terms, and then what we do is that we can just plug in our values that we've already uncovered earlier for our partial derivatives with respect to V and our partial derivatives with respect to S, and then we just drop them right into our final expression. So what we can tell from this is that we get some measurable quantity, being a change in temperature with respect to volume, is equal to our change in pressure with respect to our change in entropy. Because entropy, we can't just like stick a needle into it and go, oh, that's the entropy of the system. We have to do some sort of complex calculation for that. But now with this relationship with the partial derivatives, we no longer have to do so. We can just take some partial derivative of known quantities and get some other theoretical quantity that would be previously unmeasurable. So this is really handy. This is the first of our 4 Maxwell relations. I don't know what order Rife does it in. I can't remember what order Rife does it in, but this is the order that Fitzpatrick does it in. Here's the book, by the way. We basically just repeat this process for 3 other kinds of extensive and intensive properties, I believe. I don't remember which ones are which. But these properties are enthalpy, the Helmholtz free energy, and the Gibbs free energy. The enthalpy as a quantity is useful for describing heat transfer at some sort of constant temperature within a system. Helmholtz free energy measures the obtainable work for some sort of closed system. And the Gibbs free energy basically does the same thing, except with the caveat that we might have constant pressure or constant temperature, I believe. At least that is what I was able to discern from Wikipedia. But we're going to end up seeing and using these particular quantities a whole lot whenever we are actually assessing engines and refrigerators, which are, funnily enough, the exact same general system, just done in the opposite order. But anyway, we repeat the process for enthalpy. We obtain, or we define our enthalpy as being our energy, or internal energy, plus our pressure times our volume. When we take a differential of this particular expression, we get that our differential for our enthalpy is equal to our temperature times our change in entropy plus our volume times our change in pressure. We repeat the process, and when we repeat this process, we compare it to the mathematical definition of the differential, pick out our partial derivative definitions by juxtaposition, apply Fubini's theorem, we see that our rate of change of our volume with respect to our entropy is the same as our rate of change of our temperature with respect to our pressure. That's our second one. So we get our third and our fourth by looking at Helmholtz and our Gibbs. With Helmholtz, we define our Helmholtz free energy as being the internal energy minus the temperature times the entropy. So we take our differential, we do our direct juxtaposition of values from the mathematical definition and the differential we obtain with our thermodynamic definition, which would be these two here. Partial of f of t is negative entropy, partial of f of v is not negative entropy. I don't know why I wrote that down. It needs to be a p. Whoopsies. Let's not confuse the masses here. There we go. We apply Fubini's theorem once again, and then we get that our change in pressure with respect to temperature is actually equal to our change in entropy with respect to our volume. Which is nuts to think about. Once again, I'm reiterating the fact we are getting a measurable quantity, change in pressure with respect to volume, with respect to temperature here, and we can relate that to something like entropy, which would otherwise need to be evaluated with something like heat or the number of accessible states, which is kind of tedious and kind of crazy and oftentimes not helpful because of the sheer number of particles that we might need to be dealing with in some sort of system, or even just with changes of heat that are really, really small. And last but not least, we repeat this process one last time to get Gibbs, or rather the relationship between entropy and volume with Gibbs free energy. And our Gibbs free energy is defined as our Helmholtz free energy minus our temperature times our entropy. We apply a differential, we juxtapose the partial derivatives in those differentials with the mathematical and thermodynamic definition. We see that our Gibbs free energy with respect to temperature is our negative entropy, and we see that our Gibbs free energy with respect to pressure, partial differential, is our volume. We apply Fubini's theorem, we plug in our numbers, and we see that our change in volume with respect to pressure is actually equal to our change in entropy with respect to temperature, which is stellar. So with this in mind, we can actually begin to go forward and do things like calculate specific heats in relation to these things. And I believe that's what Fitzpatrick Patrick covers in section 6.14 if you have this book. And then Reif obviously does it in chapter 5. I don't know what section, probably like 5.3, 5.4, something like that. But yeah, going forward we can use that to look at specific heat calculations, and then eventually we can even go on and do things like evaluate things like refrigerators and engines, and look at heat transfer and the efficiency of these things, and actually begin to build thermodynamic machines, which is amazing to think about. Whoopsie daisies, we accidentally invented the Industrial Revolution, basically.